Hello, everybody. Good afternoon. My name is Edward Thomson. I'm a program manager at Microsoft. I work on Azure DevOps. If you've never heard of Azure DevOps, you could be forgiven. Until last week, it was known as Visual Studio Team Services. What we did was we decided to break it up into chunks. So, we have an agile planning tool. We have Git repository hosting. We have pipelines for build and test. And so now those are individual products from Microsoft. And Azure DevOps is the family of those tools. I work mostly on Git. Before I became a program manager, I was a software engineer at Microsoft and at GitHub, working on the Git tooling that you probably use, whether that's in GitHub or in Azure repos. I also do random things outside of work that aren't technical. No, wait, opposite. So I have a podcast about Git. It's called All Things Git. You should check it out. And if you want a sticker, I've got some. Come get them. I want to talk about Git at scale. The idea being how you can adopt Git for a very large team or a very large project. And a lot of that was driven out of what we have done at Microsoft and what we have learned at Microsoft. So when I started at Microsoft almost 10 years ago, we used a bunch of different tools, but primarily we used either Source Depot or Team Foundation version control. How many people have used Team Foundation version control? You've got to lock a file and edit it, talk to the server before you do anything, which is crazy obnoxious, right? Except if you are on a really, really large software project. Then it actually comes in kind of handy. The problem is we were building all of these sort of tools ourselves, and nobody liked them, right? Nobody likes TFVC, it turns out, because you've got to lock the files and everything. Everybody wants to use Git. And so a couple of years ago, Satya Nadella actually looked around the company and the way we were building software and realized that we weren't doing it well, for lack of a better way to put it. And so he decided that we should modernize the way we build our software. And the goal is to adopt one engineering system throughout Microsoft, a single engineering system that was using modern tooling. So we were actually using agile processes. We were using Git as a version control system, and we wanted to move everybody in the company onto that. The Windows team, the Office team, Bing, my team, Minecraft, everybody. This created a bit of a problem, though, because all of the teams throughout Microsoft had historically been doing kind of whatever they wanted. If you've seen this organizational chart of Microsoft, let me zoom in on Microsoft for you. That's kind of how it felt back in the day. Like I said, there was this tool called Source Depot, and that was built by the Windows team for the Windows team. The Office team took it and changed it, so now there were two incompatible versions of Source Depot. And then my team, the Azure DevOps team, looked at that and said, why are we building a source control system that we're not selling to customers? Our customers could use this too. So we built our own version of it and called it Team Foundation version control. So now we had three incompatible versions of the same system. And we were selling one of them. We were using two internally. And then we had teams with like a little bit of Git here and a little bit of Mercurial there. So this was really frustrating. This is perhaps not entirely accurate, but it's fair to say that we lived in silos. Every team did their own thing. They used different tools for bug tracking, different tools for version control, all of those sorts of things. And so that was a big frustration point. We were spending a lot of money to develop software that we didn't even like using. So the goal was to bring everybody into Git. And that's going to work out fine, because I read on the Git website, on gitscm.com, that Git was built to work on the Linux kernel, meaning it's had to effectively handle large repositories from day one. So, why am I even up here talking to you? It turns out that maybe Linux is a big software project. if you look at some other open source projects, Linux is big. It's about 640, 650 megabytes when you check it out. That's, when you run git clone, the stuff, the .c files, the documentation, the text files, is about 640 megabytes. Not all the history. The history, all told, for the Linux kernel is about 1.7 gigs compressed as a pack file. So that's big. It's 57,000 files. It's much bigger than Roslyn, the Roslyn compiler, which is 230 megs over about 12,000 files. And much, much bigger than Git. The Git project itself is about 35 megabytes. So Linux is big. I guess it's not at Microsoft, though. If you start looking and comparing Linux to some Git repositories around the company, my team's repository is about 3 gigs. That's, again, source, test data, lots and lots of test data, documentation, stuff like that. So we're about 3 gigs. We've got 300 people working in our repository every day. And around Microsoft, though, we're still pretty small, because around Microsoft, when we talk about large repositories, we talk about one repository, and that's Windows. Windows blows everything out of the water. It's about 270 gigabytes. Again, not history, just the stuff that's needed to build Windows and ship it to you is about 270 gigabytes. Because they've been working in a monorepo for their entire existence. And so the source for Notepad is right next to the source for, not right next to, it's in a different directory, but a SCSI driver from 97 is right next to, I don't know, Candy Crush Pro or whatever that thing's called that you can't get rid of. And it's not just like the Windows client. It's not just Windows 10. Windows Server is in there. Xbox is in there. Windows Phone is still in there. So it's big. And you might think that it needs to be reorganized, it needs to be changed. But fundamentally, when you start with something that big, that's not a day-to-day sort of thing. It's not like you can just walk in and be like, let's refactor everything and split it up into nice, tiny repositories that talk to each other over some sort of contract. Because 4,000 people work in this repository every day. You can't just say, hey, 4,000 people, go home for a week. We won't do any work. We're going to reorganize everything. It'll be fine when you come back. That just doesn't happen. So we had to figure out a way to get these 4,000 people and their nearly 300 gigabyte repository into Git. And this was a challenge for us because, so like I said, I worked at GitHub. At GitHub, we were the world's largest Git hosting provider. And we could, if somebody came to us and said, I want to stuff 270 gigabytes into a single repository, we would have said, no, we're not going to do that for you. Unfortunately, at Microsoft, when Satya says you're going to support the Windows team in their move to Git, we had to figure out how to do that. So Windows is by far the biggest challenge that we have, but we've had a lot of challenges bringing various people throughout the company into Git and into Azure DevOps. So first things first, code integration is a challenge at the scale of a few hundred to a few thousand developers working in the same repository. What we suggest to people throughout the company, what we think is a best practice is to use trunk-based development, not to use feature branches, not to create long-running, long-lived feature branches. You have a single master branch. You create a topic branch, work on it briefly, very briefly, a couple of commits, hours, maybe a day, and then you push that back into the master branch. This is similar-ish to GitHub Flow, a little simpler. It is nothing like Git Flow, which is not trunk-based development and should be avoided at all costs. Fundamentally, the idea is spin up a topic branch, write some code, create some commits, push it into master, right? But the actual fundamentals of how that topic branch gets merged is a little challenging. Because you could just run git push, and that would be fine, I guess. You might want to use code review. You might want to do some code review. You could do that outside of a pull request, maybe. But fundamentally, if we think about the way we build code and get it into production, right? We start writing some code. We build it and test it locally. We get sign-off from our peers. We get a code review. We merge it into master, and then we release it. We ship it to production. And we can use pull requests to target the middle 3 items. They're really, pull request isn't going to write your code for you, sadly. And it's not going to push it to production, right? You need some sort of continuous delivery system, pipelines for that. It's the middle 3 things that pull requests are good at. They're good at handling the build and test integration, making sure that things work well. They're good at handling the code review portion. People can comment on your code. And they're good at handling the merge. You click the green merge this commit button, and that code goes into master. And that's all good. But it turns out that pull requests have some other advantages. So when we started when we started building Git support into Azure repos, the first thing we did was build the server. And we didn't have pull requests yet. So this is how we weren't using pull requests. We wanted to. We were getting there. So for writing our code, all 300 people would just get a code review from somebody and then run git push to the server. And this broke down real quick. It's hard to think about this until you have 300 plus people working in the same repository all at once on a Friday, the last day of your sprint. Everybody wants to git push all at once. And so the workflow looks kind of like this. I'm going to clone from the server. Cool. I'm going to create a commit. Great. When I'm done with that, I'm ready to push that up to the server. So I run git push, origin master, and the server says no. The server says no because while I was working, somebody else had pushed a commit up. And so what do I need to do? Well, I need to pull their changes down and merge them with mine, or rebase them. I kind of like rebase. I'm not going to get into that argument here. And now I've got their code. I've got their changes. Now I can try my push again. And the server won't reject it this time because I've included all of the changes that are on the server. Except it's a busy Friday at the end of a sprint. And somebody else has had the same problem. And they've beat me to it because maybe they didn't have merge conflicts and I did, or their machine is just faster, or their network is faster. And meanwhile, they've put something on the server too. So now I need to pull from the server again. And if it's really a busy Friday, this can actually go on for a while. And this is not like a theoretical concern. This really happened to us. We were getting to the point where we couldn't get work done, so we started using an accelerated system for getting our pull request system done, because this just didn't work. And pull requests do solve this problem, largely, because instead of having to pull the code down, do the merge yourself, you just click the merge button, and the server does that all for you. So you don't have to worry about downloading the code. You don't have to worry about doing a merge. You do still have to worry about merge conflicts. You still have to pull the code down then and do the work then. But pretty rare, at least on our team. I mean, maybe if you guys are editing the same files often, you might want to think about breaking them up in some way if that's possible. But largely, we don't see a ton of merge conflicts. And that's great. So this drastically reduced our cycle time. So pull requests remain a best practice. I mean, they're a best practice for code review. Turns out they're a best practice for scaling your Git team. You can enforce them via branch policies. Talk more about that in a minute. But you can make sure that people are using pull requests and not going through the just running git push on the command line. So this was good, but it still wasn't perfect, especially when you get up to like the 4,000 developers on the Windows team. They actually have problems where they have multiple people pressing that green merge pull request button at the same time. They're that big. So what happens then is one person wins and 3 people lose. And so whichever person mashed it just a little bit quicker, or whichever packet the server picked up off the wire and processed first, that person gets their pull request merged. And the other 3 people don't. So what the server actually does is it will retarget all their pull requests against the new, what has now become the master branch, right? So the person who won, they're master now, they're the master branch. And the other 3 pull requests are now pointing at that. But as far as a UI concept goes, they had a green merge pull request button. They pressed it, nothing happened, got an error message, and it turns gray. And that's a bad experience. This is the way I think all other Git hosting providers work. You know, I don't want to name names. You might recognize that button. But that's not the way Azure repos works. In Azure repos, if you have 4 people pressing the merge pull request button at the same time, and they actually do press it at the same time, and so the server processes those requests, what it'll actually do is whomever got in first will go first into the merge queue. The next pull request will follow that. And so the server will actually try to merge these in order then. So it'll take what is the master branch, and it'll merge the first person's pull request in. Once that's done, it'll merge the second person's pull request into that, and on and on. And at peak times on our very largest repos with the most number of people working in them, this is actually necessary for us, especially since 4,000 person repo that's many, many gigabytes takes a little while to do the merge. So that's not ideal. That's something else we need to work on. But this is still necessary. Sometimes merge conflicts happen in here, which is frightening. And so they'll just be ejected from the merge queue. And they will then get that gray, the gray button error message experience. But it's incredibly uncommon. So we do plan for that, but it doesn't happen very often. The other caveat is that you'll note that, so when you open a pull request, if you're doing continuous integration, and I hope you are, your CI system will build your pull request changes as they would be merged into master. That can now change. So it's possible that we're actually putting code into the master branch that hasn't really been built, because we're now checking in the integration of this merge queue. And so there is a little bit more risk as well. But again, we don't actually see any build breaks in practice because of this. So that's kind of nice. Again, we can enforce that people go through the pull request experience using policies. And at scale, we absolutely have to have policies, because anytime somebody makes just a little mistake, it's human nature to make a mistake, but when you have 4,000 people working in the same repository, those mistakes add up. And so if somebody were to push code that didn't build or tests didn't pass, you'd be delaying 4,000 people from doing work until that got fixed. And so that's really not ideal, right? So we can plug into the sort of code review portion and enable policies. And in fact, we can execute almost arbitrary commands as part of the build during the code review process. This is nice because we can get as much as we can away from humans, because human nature is not great all the time. Let me give you a concrete example. So this is a change in an open source project that I work on. I work on a project called libgit2. And this is an actual pull request, and it's not a very good one. If you zoom in, you might be able to tell right in the middle, there's that test. If ODB equals null, but it's only one equals, which of course is an assignment. So we're actually setting ODB to null, and that's bad. And that caused a problem, right? But we merged it because we missed it in the code review. Even though it's really obvious right here, it turns out that this was actually a really big change. This was some refactoring. This, lots of files changed, lots of seemingly innocuous changes going in, and we just missed this one thing. And that's a bummer. And it caused a problem. And we caught it quickly and fixed it. We didn't release we didn't create a new major release with it or anything like that. But it did sneak into the master branch briefly. And that's not good. But a human missed this, but a computer wouldn't have. So we could have enabled maybe some better static code analysis would have certainly caught that. And so we've been beefing up our CI and CD on this project in order to add those sorts of things. And so one thing we've been doing is using Azure pipelines. And the nice thing about Azure pipelines is that in the Azure DevOps marketplace, you can grab like SonarQube. And you can just, it's like a one-click install to get SonarQube running. And it will find these sorts of common problems. White source is another really handy addition that you can install. If you're not familiar with white source, they do security scanning. So they will look at your open source dependencies, the open source projects that you use. And they will, they'll actually scan the versions, they'll look at the versions that you're using, and they'll compare that against the CVE database. CVE is Common Vulnerability and Exposure. It's the clearinghouse of all security holes in software projects. So when I do something stupid in libgit2, and we have like some security hole, there's a CVE assigned that describes it, and then we fix that. So by comparing the open source components that you're using against this database, you can identify when you have inherited these vulnerabilities. So white source can scan for that. So it's a nice way to add some security and stability to your right to your pull request process. And so again, these are just like one-click install in the marketplace. You can also add other tools. If there's just a command line way to do it, that's fine. That's great. So Coverity does static code analysis on C. It's very, very good. We've been using that. We've been doing fuzzing as well on the libgit2 project. And so that's something that I do on those projects. And a variety of projects throughout Microsoft take advantage of a variety of these techniques as well. So that's really nice. And the nice thing is that we can enforce that they run, right? By ensuring that people go through the pull request process, we can, in fact, ensure that all of these safety checks run. So. Let me figure out how to get out of my slideshow. Right. Let's do it the hard way. There we go. Right, so branch policies. So here I have a fairly simple C# project. It's a .NET framework app, actually. It's a .NET framework command line application. And if I want to add this validation, it's super simple. First thing I want to do is hit reload here. Right. So the first thing I want to make sure I have is an actual build pipeline. And so I can very easily add that to my repository. And it'll give me a YAML build description. I like configuration as code. There's also a whiz-bang UI designer. Don't like that as much personally. I like to be able to version my build definition. And so I could actually add in here any steps. So it's basically just running MS build and then running the tests. I could absolutely add in any sort of validation I want right here, whether that's a command line application. I could add extensions in as well. And so once that's set up, so it's going to go ahead and run the build. But I can go back to my, my repository and click right here and go to branch policies. And this is where I can add these actual policies. I can make sure that a human has seen and signed off on my, my pull request. I can look for linked work items. This is something that I find really handy. It helps you get some traceability to understand why a change came into the code base, because with 4,000 people checking in code, it's not always obvious. Why did Bob make this change? Well, Bob made it because Alice found a bug and assigned it to him. Okay, so you get that traceability from the code back to the actual work item. But the thing that I think is the best is the build policy. So this will use the pipeline that we just created. It will make sure that it succeeds. So the build has to succeed and the tests must pass before I can merge a pull request. And so this is incredibly handy. I can save those changes. And now if I were to open a pull request, it would not allow me to merge it until the build actually succeeded. So that helps us make sure that, that we basically keep the master branch healthy at all times. And that's critical when you have, it's critical for any size development team, but it's especially critical when you have so many developers. Wow, I really closed that. Right. Great. So the other thing that we see a lot of with repositories around Microsoft is repositories that have large files in them. And this large files are not ideal in Git. It used to be that we would see maybe on the Windows team, back when they were using Source Depot, that they would actually build something and then check in the build results. And that, oh, that's painful. So please don't do that. But we do still see a lot of repositories that have legitimately large files that need to be versioned in them. I work in Cambridge, England, and the Microsoft office there is actually a Microsoft research office. So they're the ones that actually came up with HoloLens. So they do a lot of computer vision. They do a lot of AI and ML. And that always means big corpuses of test data. So they've just got big files for images and stuff like that for tests. Sometimes you'll see artwork going into a product, and that might want to be version controlled. Sometimes you see a nice application that has a help video. And you want to version that help video alongside the code that it describes. So there's nothing wrong with large files. It's just that Git wasn't really meant to support them. So the problem isn't even a single large file. It's multiple versions of a large file. Because when you run like git clone, you don't just get the most recent version of a file. You get all of the history. Yeah. Thanks. One of these days, I'm going to have to learn how to use PowerPoint. There we go. Right. So it's the multiple versions of large files, because when you run git clone, you get all of the history. So that means you get all of the versions of the large files. You don't just get the most recent one. Because clone, like the name implies, gives you all of the data. It gives you a full copy of the repository, which is great unless there's binaries in it. So you get all of these commits with all of these files in it, and if those files are a 100 megabyte ping, Now you've got 4 100 megabyte pings, and you probably only care about the most recent one. It's rare that you're going to want to, I don't know, diff 2 versions of a ping. I guess it's possible. So the idea is to get these files out of the repository, out of Git itself. And so you can use a technique called GitLFS. GitLFS does exactly that. It takes the binaries out of your Git repository and replaces them with what's called a pointer file that describes where it can find the actual binary itself. So what goes into the Git repository is this tiny little text file that's just got some metadata. And GitLFS, when you check out the repository, GitLFS will read this file and use it to locate the actual binary. And so it will basically bring these binaries into your repository on demand. It's very clever. It's what we recommend people use for large file support. Right. There we go. Great. And of course, my VM fell asleep while I was talking. So GitLFS is, if you're using Git for Windows, it's available. It actually comes as part of the installer. You just need to check that box. Otherwise, it is a separate installation. If you're on Mac or on Linux, your package manager will have it, of course. Great. So I've got a repository set up already. There we go. So this has got, I think, 1,000 1 megabyte pings checked into it. So there's only 10 in the most recent version in head. There's only 10 of these, but there's 1,000 overall. So right now I'm cloning, well, 1,000 1 megabyte pings. And it's not going very fast. It's actually going faster than I expected. Conference internet in Australia, I didn't expect to be this fast. But it's still not great. So these are just checked in the normal fashion. I've also got the same repository with the same history checked in, only this time I used GitLFS. So if I clone that one instead, it's going to give me the same sort of thing. Oh, and so that receiving objects went incredibly quickly. That's where we were stuck last time. Now it just pulled down 2,000 files because it's just those tiny little text files this time. Those LFS pointer files that describe how to get the contents. And then the next line is filtering content, 10 out of 10. So it brought down the 10 files that I have here in my, sorry, let me go into the repo, here in my repository. And so you can see, actually, let me just, if I open up one of them, it's the Git logo. That's cute. So there's another technique that you could use that some people like, where instead of cloning the entire repository, you just get the most recent version. And at a glance, it feels like these are sort of the same technique. Instead of using LFS, you could just commit all your data, all your big files normally, push it up, and then do a shallow clone, it's called, to get just the most recent version. The problem with doing a shallow clone, though, is that you can't run git log and see anything, because you only have that one commit. You don't have all of the rest of history. And so by using LFS, I can still run git log. I can also check out previous versions. Because again, with a shallow clone, I won't have this data. Now, I can go back in time and I can check out old versions. I can go all the way back, in fact. And what will happen is that GitLFS will just page in the missing data. Right? So now if I open this file, I think I had a blue background before. Whoops, sorry. I think I had a blue background before. No, I had a red background before. Now I have a blue background. And so I can go back to different versions. And now I should have, now I should have that red background. Yeah, there we go. So GitLFS is a really nice technique for that. Great, all right. So large files are one thing, but we actually see a lot of repositories around Microsoft that are just big, right? The Windows repository itself doesn't have a lot of really large files in it. It has some, but that's not its problem. Its problem is that it's just big. And so we had to come up with some other strategies to cope with that. We thought about splitting it up. I'm not sure what to do with the 300 gigabyte repository. Do you split it into 301 gigabyte repositories? That's a pain. Do you split it into 30 10 gigabyte repositories? That now you've got 30 repositories and they're still really big. We thought about trying to do some clever things with submodules. We actually spent a lot of time convinced that we could make submodules not be terrible, but we failed. That one's on me. But fundamentally, we needed a solution. So again, the problem is that when you clone a giant repository, you get all of the history. And even if you don't do that, even if you do that shallow clone that I was talking about, with 4,000 developers, that gets really expensive really fast. And even if you ignore history for a moment, even just working in the repository, it's really slow. When we first looked at Windows, we just dumped it into a Git repository and said, how bad is this gonna be? And it was bad. It was real bad. We cloned it. We ran git clone. It ran for a couple hours, and we were like, oh man, this is painful. And then we realized that it had failed because like the network had gone out. So we tried it again, and we let it run overnight. And 12 hours later, we had a repository to work with. And it took, 3 hours to switch branches. It took 8 minutes to run git status, and that's when we hadn't changed anything. So it took 8 minutes to scan the disk and go, nothing. So this was not ideal. The solution that we came up with, I thought was crazy, but my colleague Saeed was convinced that it would work, and in fact it did. It's something that he called, at the time, GVFS, the Git Virtual File System. Now it's called VFS for Git. Turns out there's another GVFS. We didn't do a lot of homework when we were naming it. We were just like, what are we gonna call it? Well, it's a virtual file system for Git. Let's call it the Git Virtual File System. Once we published it, we were told by the GNOME project that there was a GNOME virtual file system. So we changed it to VFS for Git. You'll still see GVFS a couple places here, so I apologize for not having gotten everything done. The idea behind VFS for Git is largely that we want to make every command in Git run in linear time, or not quadratic time at least, against the number of files that you are working with, not just the number of files in the repository. So if I'm hacking on Notepad, I don't care about that SCSI driver from the 90s. I don't care about Xbox. I only care about the Notepad source. And Git behaves much closer to the speed that I would expect for the Notepad repository and not the entire Windows repository. And we were largely pretty successful with this. We were able to get the time that it takes to clone the repository down to 90 seconds, which is pretty impressive, actually, considering it took hours before. Switching branches takes about 30 seconds. Running git status takes about 8. That is really what we measure. One of the things we measure most is git status, because you run it all the time. I don't know if you've ever, if you replace your git status command with like a 30-second sleep, it will drive you absolutely crazy. 8 is still too slow, but we're making headway on that. Adding a file takes 5 seconds. Committing that change takes another 5. So 10 seconds to just add a file and commit it. So this is very workable. And if you're going, wow, that's really slow, it's actually not that much worse than Source Depot was, or TFVC. because a lot of those things talk to the server, right? So you've got some network latency involved. So this is enough for us to have moved the Windows team over, and we did. So the Windows team is now entirely using Git, using VFS for Git. So we're really happy about that. The way VFS for Git works is that instead of running git clone, you run gvfs clone. That's the only weird command, because it needs to set some things up. And instead of getting the entire repository, you get sort of the equivalent of a shallow clone, except you don't get any of the files. So you get the metadata, you get the history of a repository. So you get and not even very much of that. You get a couple of commit objects, you get all of the tree objects. Those describe the way a repository gets laid out, but you get none of the blobs, you get none of the actual file contents. And as you work with the repository, we throw in this sneaky little layer into Windows, above the file system and below the application layer, to intercept calls to files, and then we pretend like they're there. And when you open them, we actually go and get them. So we add, a normal application just talks straight to the file system using the Win32 APIs. Windows has the notion of a filter driver. So we plug in at that level. And a filter driver basically gets to intercept every Win32 API file system call and decide what to do with it. This is how your virus scanners work, right? When you go to open a file, your virus scanner can add a filter driver, and it can say, hold on, I'm going to actually read that file on disk, make sure it's safe. OK, everything's fine. I'll get out of the way now. Instead of doing that, when you enumerate the directory contents, we pretend that these files are there. We tell the API to return these files, even though they're not actually on disk, because we didn't clone them. When you actually go to open one of the files, just whether that's on the command line, whether that's in Visual Studio, we'll actually intercept those calls too, download the contents from Visual Studio, from Azure repos, pardon me, and then put the file contents on disk. So subsequent reads are fast because the file contents exist, but they don't actually need to be there the first time you open a file, as long as you're online. So we'll do that with subsequent files too, and it's surprisingly good. Downloading files on demand doesn't seem like it would be particularly fast, but it works out surprisingly well. Certainly well enough for the Windows team to be using it. So I'm going to, there we go. Don't want to have to type that URL. So I've just got a Git repository here. Again, this is libgit2. This is the open source project that I work on. So there's nothing particularly special about the repositories that VFS for Git uses. And again, it's still called, the command line is still called gvfs for legacy back compat. So I'm gonna gvfs clone this down from my Azure repo, and it's gonna clone just the information. Again, it'll say here commits and trees. So just the metadata about how the repository is laid out. And then it's going to set up the actual filter driver. And so I can go into my directory. And actually, that was really fast. Usually the first time when you run dir, there's just an almost imperceptible lag while it goes and fetches some information out of the Git repository. Let's see if nope, super fast. Wow, OK. But so these files don't actually exist on disk yet. They look like they do, right? There's nothing special. This isn't a special command line that needs to know how to talk to VFS for Git. These just appear to exist. And I can even open up one of them. There, you'll notice a slight lag. So what it's done is it's actually downloaded the file contents and put them on disk. And I can edit this. I can make changes to it. I can do whatever I want. And certainly I interact with my repository as if it's really there. I can stop the filter driver. I'm going to GVFS unmount. There we go. And now we see what's actually behind the curtain. So I've got a couple of files. VI read the .editor config. That's cool. Git attributes is needed to know how to put files on disk. This README was the one that I opened, and I navigated into the source server, so it actually created that. But there's nothing else in there. So it's a surprisingly effective way to avoid having to download the entire repository. And it works because most people don't work across the entire Windows source tree. Even the people that are working at a very low level and doing cross-cutting concerns still are only touching handfuls of files at a time, certainly not the entire 300 gigs. If I GVFS mount, that'll start the filter driver again. It'll take just a second, and now I've got all those files back. It's pretty crazy. Again, I didn't think this would work, and yet my colleague Saeed absolutely proved me wrong. So I'm very impressed, and this is what enabled the Windows team to move over to Git. So they use Git with GVFS. Again, I'm still, even as I say it now, I'm still surprised how well this works. It has a number of advantages, like we can basically use stock Git. Aside from the GVFS clone, after that, it's a regular Git repository, because Git reads files on disk just like Notepad or VI does. So it doesn't really require too many special changes. We have been making changes, and we are committing them back. We're publishing them back to the Git project itself. So we're a little bit ahead of that with our version of Git. But by and large, when somebody runs into a problem using Git, they look it up on Stack Overflow, or they ask a friend. They don't need to know something special about GVFS. So it's incredibly handy. There are limitations, of course. You've got to be online, at least the first time you open a file. Subsequent uses, you can be offline. I've been building version control systems for a long time. We always used to talk about the developer on a plane. It feels a little outdated now since most planes have internet. But it does work pretty well even in the developer on a plane scenarios. Where you don't have network access, as long as you have gotten the files that you're interested in working in. And so a lot of people will sort of precede what they want. So if you're working on Notepad, you get the Notepad dir, and you've got everything you need. Right now, it only works with Git. It doesn't work with libgit2 or jgit, which are alternate libraries. I'd like to see that, but it's not. As one of the libgit2 maintainers, it's not super high on my priority list, so we'll see. And some commands don't work. You can't run git grep. If you've never used git grep, you can say git grep foo, and it'll show you a list of the files that have the word foo in it. That's great. In order for that to work, the files need to be there. So if you ran git grep on a GVFS repository, on the Windows repository, it would download all the files. That's not good. So we've turned that off. Frankly, if you're trying to grep through 400 gigs of source, you probably want the indexed fancy search that we have on the server anyway. So it's not a big loss. It is open source, and it is, at the moment, limited to Windows. We're working on a Mac version now. The Linux version, we're working with GitHub to build. So. And I don't have an ETA on that. And it is largely only on Azure repos. There is a Bitbucket plugin, and GitHub has announced that they're going to support it, but as far as I know, they have not yet. So it's still heavily Windows and Azure repos. We'd like to see that continue to grow, though. And the open source community is helping to drive that, so that's very exciting. That's not the only thing that we needed to do, though. We actually have to make changes to Git itself. And a lot of this is around assumptions that were made about the size of repositories that would exist. Quick history lesson, I'm sure many of you know this. The Git itself was built by Linus Torvalds to manage the Linux kernel. And so largely, it reflects that ecosystem. And so as long as Git could handle the Linux kernel itself, that was considered, probably good enough. Not good enough for us, unfortunately. So we actually have had a really amazing hire on the team, Derek Stoley, and he's written about a lot of the changes that he's made to Git to enable it to go faster. Derek was a mathematician before he became a professional programmer, and he's actually a graph theorist, so perfect for working on Git. So somebody coming in with knowledge of complexity theory and graph theory is amazing. And so a lot of these things are just basic computer science-y kind of changes. If there's a function that's quadratic, can we reduce that to something simpler? And so there's a lot of time spent sitting in a profiler, identifying hotspots, and just aggressively going in and reducing those. We've made a lot of headway there. There's also some problems when bringing Git over into the world of Windows. Because again, Git was built on Linux, for Linux, primarily, by people who knew Linux. There's not a lot of people working on the core Git application itself that really are familiar deeply with Windows. And so Git for Windows exists as a separate fork and is managed separately. And there's a lot of work that goes into it to make it work. Because Git, it turns out, is it's a lot of things. It's in the spirit of a Unix application where you have small separate programs that do their own things. If you run git space add, what that really does is it goes and finds an application called git-add on the system. And so there's a git-add, there's a git-commit, there's a git-status, and all of these programs will actually talk to each other, like good Unix programs often do. And that's great, but not so much on Windows. The reason Git for Windows is what it is because some of these applications are not native code. They're written in shell scripts, for example. And so you need a bash interpreter. So when you download and install Git for Windows, you get bash. And bash isn't very useful on its own because shell scripts do things like call awk and sed and cut and all these other three-letter Unix commands. And so those need to come along for the ride as well. What's worse, though, is something that's sort of different about Windows compared to your typical Unix system. So, let's see if we can get back to Windows. Great. And that is executing processes, creating new processes. Turns out it's a little bit slower on Windows than it is on Unix. So here, I've got a rather simple application. This is a simple C application. It's going to call this other command, noop.exe, 1,000 times. It's just going to execute it 1,000 times in a loop. What does noop.exe do? Well, as the name suggests, not very much. Return 0. Simplest C program you can have, right? I guess I could have made it simpler by writing an assembly or something. But no, simplest C program you can have. So let me go ahead and start that up. I'm gonna, if I can remember my PowerShell, yeah, exec.exe. Great. So while that's going, let's go do the same thing on Mac OS. I have the exact same program, exec.c, noop.c, cool. And we'll time that one. About 4 seconds, okay? Let's do the same thing on Linux, where Git was created. Okay, there we go. Oh, that was unbelievably fast. I don't even believe it was doing any work. Let's put a printf in here. I wanted to avoid I/O because I/O can slow things down. Okay, and we'll build it. And we'll throw in some optimization. It's got some warnings we can ignore. And yeah, for real, it's doing work in a second. Okay. Yeah, the Windows one isn't even done yet. So when you have an application, a system like Git that interacts with other applications just by calling them and parsing their output through standard out or standard in, you can understand how this could get slower, like a lot slower. Rebase is one of the really guilty parties, as is Stash. They're both heavily shell scripted. And so the maintainer of Git for Windows, Johannes Schindelin, has been going through and changing this to be more C, more native code, and less shell scripts because, again, shell scripts are slow. There we go. 110 seconds. Yeah. 110 versus 1. So you can understand why he's doing that. So Rebase and Stash were recently rewritten as C, native code as quote-unquote built-ins. And you can enable that in Git for Windows 2.19, which just came out the other day. It's still experimental, gotta warn you, but it's a big performance boost. And my computer's fans are all running just from trying to exec a couple processes on Windows. So not an ideal situation. So it is something that we've had to invest in at Microsoft. And I'm really happy to see that we leveraged Google Summer of Code as well. I'm really happy about that. So pretty much out of time. I'd be happy to, if you have questions or just want to chat about Git and performance or Git and scale, I would be very happy to hang out and talk. Feel free to hit me up on Twitter also. I'm at eThomson. If you were at Barry Doran's talk yesterday, he mentioned that his Twitter is mostly swearing and dog pictures, and I'll make the same caveat just before you jump in and click the follow button. But otherwise, yeah, thanks so much for coming out, and feel free to be in touch.